Good morning. Today we are going to discuss orchestrating Cassandra with Kubernetes Operator and PaaSTA. And welcome again to Percona Live Online. And also want to give kudos to Percona for organizing this online conference before proceeding. So let's start. Okay, so about me. So I'm Raghavendra Prabhu. This is my email address, rprabhu@yelp.com. And a random surfer is my Twitter ID, etc., etc. I work as senior software engineer at Yelp, and I've been working here for about 4.5 years. I work in the team known as Database Reliability Engineering, and that's our logo. I work in the London office in United Kingdom, but our team is distributed and is based also in San Francisco, California. And so what do we do as a database and reliability engineering team is we deal with databases. Of course, that's not a surprise, right? I guess. And so we deal with databases such as MySQL, Cassandra, and Zookeeper. Quite critical. So what is Yelp? Yelp's mission is connecting people with great local businesses. As you can see there, on the right-hand side, you have a great local business, and on the left-hand side, that's you. And what we do is we connect you. So let's do an overview of what today's talk is about. So it will start with a brief introduction to distributed systems in general, I guess, and then I'm going to speak about Cassandra and Cassandra at Yelp, followed by a brief overview of orchestration itself, then the core of the talk, which is the Cassandra Operator, and then finally, I'm also going to talk about a few opportunities and challenges that we observed during this, and followed by conclusion. So let's start with the introduction. So I often start my talks with an introductory quote, actually. So Leslie Lamport, who's a distributed systems guru, stated once that a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable, and probably users of that computer miserable as well. So, and this is none more true when you notice or when you manage distributed systems in production. And this comes into play when you're focusing on the orchestration of a distributed system as well. So what are the having spoken about that quote, let's see what are the desired traits of distributed systems. In my opinion, desired traits are like reliability, scalability, and maintainability. Reliability is something, it should work even in the absence of faults, human or technical faults. It should be reliable. It should not fail that easily. Scalable is that it should be able to scale with concurrent and often contended workload, and allow for horizontal as well as vertical scalability. And finally, maintainability, which is often very underrated, but very much important when you need to scale system with the organization. Maintainability more or less deals with operability, simplicity, evolvability, extensibility. Basically, maintainability is the one that you think about when you're designing a system for a long time. Something that can span multiple teams, it can span multiple years, and whatnot. And I want to give kudos to Designing Data-Intensive Applications book, which provided the contents of these desired traits. In fact, the book mentions that these are the traits of a system rather than a distributed system. But again, what system is not distributed these days, right? So, having spoken about desired traits, let's do a quick tangent on distributed system fallacies proposed by Peter Deutsch of Sun Microsystems quite a while back, even when the distributed systems were not as prominent. So, understanding these fallacies is important when dealing with distributed systems and being aware of its imperfections. More importantly, these fallacies are very important to keep in mind when you're designing an orchestrator or a distributed database, an orchestrator which itself is distributed, And So just to go over them briefly, things like network is reliable, latency is zero, bandwidth is infinite. None of these are true. But again, much like all the fallacies in real world or biases in the real world, we often tend to stumble upon these things. So it's good to keep this in mind when designing, especially things like one administrator or zero transport cost, homogeneous network, which should be pretty self-evident that it is not that straightforward, and topology doesn't change. Again, that's something that I've seen multiple issues recently as well. Topology does change. So I'll be referring to some of these fallacies throughout the talk. So keep an eye out. Okay, great. So we spoke briefly about distributed systems. Let's talk about Cassandra at Yelp. So what is Cassandra? So when I'm speaking about Cassandra, I'm not talking about the Trojan War, though the name Cassandra was inspired by the daughter of Priam. She could see the future, but nobody could believe her. I guess only the name carried to the name of the database. Of course, we all believe Cassandra. So Cassandra is a distributed database, and this is its logo. So it's a distributed wide column NoSQL data store. And it is leaderless / multi-master, which means you don't have one master and replicas, but all the nodes can either directly take your connection traffic or act as coordinators, which makes it much more amenable for orchestrating. It makes our job easier, basically. And it has a multi-region support, very important for companies, which are distributed across multiple regions. And it provides tunable consistency, which means the client can say what level of consistency they need, whether they need all the nodes, some nodes, one node, or any node, things like that. It's very much optimized for writes, as opposed to say like MySQL's InnoDB, which is very well optimized for point reads, say. And it's also very cloud aware, and it's getting even more cloud aware if you see the announcements from DataStax recently. So it has support for gossip, for propagation of topology information, and so on. And then it has a very good failure detection mechanism, or what is known as a fee accrual mechanism. Very interesting. It is topology aware, so it understands the concept of racks, data centers, and regions, and so on. And it also has it also facilitates aspects such as hinted handoffs when nodes die, their neighbor nodes take care of those reads, and then they give it back to the neighbor when the neighbor comes back. So things like that. So Cassandra at Yelp. So Cassandra at Yelp is used for both primary and derived data. Primary data is one where you directly store it. Derived data is one where you store in another database, and then you connect these two databases with a pipeline, like a data pipeline, and make the data flow from one to another. And similarly, it's also used for OLTP and OLAP use cases, online transaction processing and online analytical processing, wherein we look at latency and throughput, respectively. So it is, in terms of use cases, we use it for all kinds of applications, batch and interactive applications, web serving microservices, analytical applications, metrics, caches, and for also tracing purposes, for storing the tracing data. It's a very much important component of our stream processing pipeline as well. Much like all the things these days, it's deployed on Amazon Web Services. And what we use for storage is we use EBS, which, even though not explicitly mentioned, it's network attached storage. Not very far from the instance, but it is network attached, very well optimized storage. And this is important because it provides us, it helps us in the separation of stateful and stateless components. And this is very important when it comes to orchestrating something like databases, because laws of physics, right? If let's say they're tightly coupled and you need to say move the compute around, you will need to spend a lot of time moving the data also, which is not desirable. Whereas AWS provides a very robotic way of detaching and attaching these volumes from instances, very out of the box way. which is very good. Coming back to Cassandra at Yelp, we use automated schema management wherever feasible. We also for backups, instead of doing some level of backups at a Cassandra level, or something like rsync. We make use of our deployment, which is AWS, and we use EBS snapshots, which work pretty well, and are not as complicated as one might think that they can be. And we use currently with the EC2 one, we use Zookeeper for cluster coordination for like restarts and so on, but that is changing. Great. So let's see. Okay. So you have Cassandra at 100,000 feet. So this is how it looks. So we have what is known as a multi-region cluster. And so this is the status quo with the EC2. And I'm going to show you the Kubernetes one soon. So the way it looks like is we have a cluster in two regions, US East 1 and US West 2. So as you can see from distributed system fallacy perspective, you have both the LAN as well as a wide WAN, connecting these two clusters. This one cluster. Keep in mind, this is one cluster in two regions. So latency can be very important. And remember that Cassandra is leaderless. So both of them can take writes for each of them. And things like bandwidth is constrained between the regions. Latency can be highly variable. And network can also be quite heterogeneous. And now, if you zoom into one of the regions from 100,000 feet to 1,000 feet, you can see something like this. Now, what is this? What you see here is the AWS region with two availability zones, and 6 nodes of the same cluster are spread across the availability zone in a round-robin fashion. What we can see, they're also attached to elastic block devices. They do EBS snapshots. So this is the one how it looks with the EC2 for multi-AZ multi-region Cassandra cluster. Now let's look at each of these regions in detail soon. So having spoken about Cassandra and Cassandra at Yelp, let's speak about orchestration. So what is orchestration? Let's see. So orchestration is defined as the automated configuration, coordination, and management of computer systems and software. That's what Wikipedia says, But if I have to define an orchestration system, let's look at why we need orchestration to begin with. Now, any business, web service business kind of looks like this. Looks like the chap there on the wire. On one side, you need to be fast. You need to deploy things fast. You need to scale fast. You have a lot of churn. You have a lot of new things. On the other hand, you need to be safe as well. Your users, want a reliable service, right? It needs to be consistent. It needs to be available as well, and the absence of network partitions, of course. But for the users, it means that they need a service which provides correct answers and is up all the time, right? So if I can sum up the goal of an infrastructure team, it would be to deploy new features, infrastructure changes, and scaling the cluster while that cluster remains available at all times. And this is where a good orchestration mechanism is very useful. So let's come back. Let's talk about orchestration itself. Orchestration, as I said, is the automation of coordination, configuration, and management. And so that's like a very long definition. If I have to choose one, I would say that it is the operationalizing of the learnings and the principles associated with management of a system. So let's say you have a system and you manage it. And every day you manage it, you learn new things on how best you can do it. And instead of writing it in a run book or so, though in some cases that's the only alternative, it's always best to automate it. It's always best to convert it into a set of rules which an orchestrator can deploy and use. So that's what I would call as an orchestration system. Now, speaking of why orchestration, as we mentioned in desired traits, you have reliability, scalability, maintainability, and maintainability is one where I would say orchestration system pays rich dividends. That's because architecture keeps evolving all the time, and by ensuring that the principles are maintained in an orchestration system, it becomes more maintainable over time. Time is a great stressor, as Nicholas Taleb once says in his Anti-Fragile book. So again, yeah, so it is why orchestrate. You need sustainable management of constantly growing infrastructure. Sustainability is the key there. And again, automation of best practices and learnings. So in our case, one more thing to keep in mind is what is known as a control plane. Control plane is, in plain words, is the way in which configuration information is generated and injected into a system. Now, having an orchestration system and a control plane which are dovetailed into each other very nicely is a match made in heaven. And that's where our Cassandra operator and our ingrown, homegrown platform as a service and Kubernetes come into play, because that provides us as a complete package of orchestration system as well as the associated control plane, which work very well with each other, which understand each other. I'll go into each of them in detail soon. So this is how our present orchestration model looks. And as you can see, it has, we use a lot of configuration management systems, popular ones, Terraform, Puppet, Git. You have Cassandra on the other end, and we interact with, each thing interacts with the other all the time. And yeah, this is how it is. So this is where we want to go, ideally. And so this provides a single transitive control plane. And instead of interacting directly, we use Git as the primary control plane, and the Cassandra operator uses Git and talks to the Cassandra running on containers. So this is let's discuss this one by one, and this is how the orchestration stack looks like. And so as you can see, there are 3 layers. We start with the platform as a service, the Kubernetes, and then right on top, it's the Cassandra operator. Let's talk about Kubernetes. So Kubernetes is a container-based, popular orchestration system, and open source, actively developed with several cloud providers such as AWS as contributors as well. They often have their own deployments of Kubernetes, so they actively contribute to open source. And it has well-defined building blocks, implementing several best practices for distributed systems like rolling restarts and so on. So it has support for both stateful and stateless applications. It organizes the containers into what are known as pods, which when I talk about the Cassandra pod, it will become more clear. And more importantly, it integrates pretty well into our platform as a service. Platform as a service is nothing but, it's a category of cloud computing services that provides customers a way to manage the distributed system. And mature infrastructures such as ours tend to have like a platform as a service, which tends to be quite opinionated, idiosyncratic, and quite specific to that organization. On the other hand, Kubernetes is quite generic. Now, had it not been extensible, it may not have been that easy to, implement and integrate it into our platform as a service or use it for Cassandra. But since Kubernetes is quite extensible, it can be tailored to our organization's infrastructure and our platform as a service. So next is the PaaSTA, which is our platform as a service. It's a highly available distributed system for building, deploying, and running services. And it's used for both stateful and stateless microservices. We have thousands of microservices deployed and growing. We don't have a way to constrain anyone from not deploying any service, though we have ways to keep tabs on their resource usage. We have hundreds of deployments every day. Again, none of these are gated in any format. Anyone can deploy anytime. So PaaSTA handles compute, storage, and network abstractions via Kubernetes, which means the compute, like number of CPUs, the disk, local storage, and non-local storage, and network abstractions like CNIs, which are network interfaces in Kubernetes. Now, in addition to this being our main platform as a service, why PaaSTA? So there are a couple of reasons. One is when you are again coming back to the maintainability aspect of it, the having common abstractions for managing your services, be it databases or some USG service or a Apache service or an Nginx service, is very useful. Which means when you're restarting a service, let's say you're restarting a web server, you're using like a command provided by a platform as a service. Like let's say in this case it's PaaSTA restart. Having the same thing, doing the same, having the same interface for restarting a database can also be very useful. It considerably lowers the learning curve for new and new engineers and even the old ones. So in addition to that, we also use some of the things provided by PaaSTA natively, things like spot fleets for time shared instances, which can be revoked anytime. And it's not like we use this for our critical infrastructure. We use these for let's say for test systems or large systems in non-production, or for backing the services associated with tracing, for instance, which can provide a significant cost savings. And Clusterman, which was recently open sourced, is our in-house signal-based autoscaler, and that has been quite useful with Cassandra as well. And one more thing to note here is that PaaSTA also provides us a way to easily diversify across multiple AZs and instance types. Instance types being very useful for the spot fleets, and this is for high availability. And now let's talk about Cassandra Operator itself. Cassandra Operator. Oh, here he is, or here she is. So Cassandra Operator has been developed by DRE team at Yelp. And why? Because much like our platform as a service, we needed an operator which understands our infrastructure, which is quite again idiosyncratic with respect to our infrastructure deployment, which integrates very well. And at that time, at least, there was no other operator which provided this functionality. So it provides a control loop for reconciliation, in short. And I'll talk about the loop soon. And it provides what is known as a custom resource for Kubernetes. It defines, it's like a custom resource is nothing but the whole package. And in the package, you define things like what is stateful set, which manages the containers and their life cycles. Then you provide container spec, things like what does a container specification looks like, and then the storage side, and so on. So that's the custom resource for Kubernetes, in short. And of course, the operator is written in Golang because a lot of the Kubernetes infrastructure, Kubernetes ecosystem is in Golang. And the operator is defined in Kubernetes itself. It deployed in Kubernetes itself. It's not deployed outside. That's what I mean. And more importantly, and this is something that I noticed while reading a paper from AWS, it also provides us a big red button, which means that let's say this operator is doing something and we want to step in and do something, right? So we can always pause the operator and do our things rather than both of them working on it at the same time. This is very important when you're developing an automation system. Always have a pause button. In terms of responsibilities, in short, it creates cluster from the specifications. The specification looks like that on the right-hand side. I'll show another specification soon. It provides us the way to scale the cluster up and down from the Git specs. It provides safe and, very importantly, reliable change deployments. Remember, these deployments happen all the time, so it's very important that they need to be safe and reliable. It also provides lifecycle management, which is that when nodes die or are born, it provides us a way to add them to the cluster safely. It provides multi-region coordination, credential management, the TLS certificates, and it also provides the way to optimize resource usage. while keeping availability in mind. So in short, before we go further into the operator, let's see what's there in a Cassandra pod. A Cassandra pod is like a, much like a pod in the real world. It has like a cluster of seeds, except in this case it's a cluster of containers. And in this case you have like one main container usually, which is what is known as the Cassandra container, running the server process. Then you have sidecars. Sidecars are nothing but processes which are helpful, helper processes, like HHcheck for smart stack, which is our discovery mechanism. Then we have cron jobs container. Then we have a container. Then we have a container for alerting and observability, which in the form of Prometheus exporters. And then we have a container for change data capture, which is for obtaining stream of data from the Cassandra itself. And more importantly, these sidecars can be configured dynamically as well. And we have a way to do that, because not every cluster may require, let's say, a change data capture publisher. Storage, aka state. No discussion of databases is complete without discussion of state. So we use EBS for Cassandra. It provides, as discussed earlier, without going into detail, clear separation of stateful and stateless, and quick healing up on node failure. On the right-hand side, as you can see, there's a picture wherein, when the node dies, the container gets evicted onto node B from node A, and the storage gets detached and reattached in the same availability zone. And we use the dynamic provision of EBS with Kubernetes, which means we have a storage class per cluster, and compute follows data, which means the compute follows data should be evident from the picture again. And this happens across multiple availability zones as well. So having spoken about the operator and having spoken about the storage, so we saw what the operator is, we looked at what is in the pod, we looked at the state. So let's put it all together. What is a reconciliation? Reconciliation can be defined as, you have like two states, so state A and state B. State A is where you are, state B is where you want to be. And taking you from state A to state B is the job of the reconciliation. It brings the two states together. And and the way it looks like is the operator, constantly observes the configuration in Git for any changes. It constantly listens to the cluster for any cluster events like node dying and so on. And it integrates both these observations and tries to update the cluster state, in a continuous reconciliation loop. And this is how the cluster specification looks like. As you can see, it shows things like a number of replicas, the cluster name, CPU, memory, disk, what kind of JVM options if required, monitoring options, Cassandra configuration, and so on. And in brief, the reconciliation loop looks like this, without further elaborating here, which is that it checks if there is a stateful set exists. If it exists, it creates it. That's very simple. Now, if it does not exist, it needs to check if something has changed in the specification, in which case it updates the specification. If nothing has changed in the specification, but it has to scale up the cluster, we handle this differently compared to other parts of the specification. If the cluster is not ready, usually we don't try to scale up the cluster. This is more in line with the what is known as a precautionary principle. It says that do no harm, don't scale up the cluster if something is wrong with the cluster. First fix that and then scale up. And then for scale up, it looks at if the cluster is ready, and then proceeds by scaling up one by one. We don't scale up the cluster from when going from like 6 to 9. We don't directly go from 6 to 9. We go 6, 7, 8, 9, and we do health checking in between, just to ensure that we don't break anything and we can easily roll back if required. Similarly, for scaling down, this is slightly different because we need to decommission the pod. Remember, this is a database, so you need to tell the cluster that this pod is going away from the cluster, and you need to decommission it. Now, putting it all together, this is how the region picture looks like with the operator. And yeah, as you can see, the few things have changed here. You see the availability zone, And you have, instead of like EC2 instances, you have containers, but you have the same EBS attached to it. You have the Kubernetes, you have the Cassandra operator, and then you have these snapshots. And the platform as a service provides the glue between the operator and Kubernetes. Now, with the same operator, the Yelp Cassandra looks like this. You have the operator on both regions with managing its containers, and it uses etcd for coordination. This is required because our Kubernetes is a non-federated setup, which means the Kubernetes in each of the regions is separate. So you need a etcd lease mechanism so that for the same cluster, more than one operator is not operating it at the same time. Too many cooks spoil the cluster. So this culminates the discussion of the operator. So let's briefly go over opportunities and challenges. I'm going to mention 3 of each. So the first opportunity, let's start with opportunities, the glass half full. So the first one is it provides is a very granular cost accounting mechanism, which means that we can see precisely, or at least try to be more precise in how much CPU is being spent, how much requests are being served by this CPU. And this provides us a way to think about our Cassandra deployments in a more efficient way and to tune it accordingly as well. It also provides us, things like AutoScaling, because load, web traffic load can be quite cyclical in nature. So we don't want to burn AWS cycles when there's no load. So with this, we have both easy to tune knobs for manual scaling. When you want to scale up CPU and memory, like there is a holiday and people are going to use it more. So you scale up in advance, or do auto scaling. And currently, things like horizontal scaling and vertical scaling. Vertical scaling being where you increase the CPU and memory while you bounce the pod. The horizontal scaling is being one where you add more nodes. Now, horizontal scaling is very useful when you're thinking about long-term capacity planning, whereas vertical scaling is more useful from a short-term perspective, for short-term spikes or for spikes lasting an hour, say. Security, this is very much understated, but reduction of surface area by moving something into a container has been very useful to us, because we can define things like IAMs, identity and access management, on a per container level. We use what is known as a KIM for this. We also tightly, fence the container, the Cassandra container with Linux capabilities. We restrict it. We don't run anything as root, for instance. And there's no unprivileged user. And we also integrate it with pluggable authentication or authorization mechanisms, and so on. Now, having spoken about opportunities, let's see about the challenges. Now, just to clarify, these are the challenges which added, let's say, spice to our development. These are not blockers. These are not some things which discouraged us. In fact, this made us think differently, made us innovate. Innovation comes in the face of challenges, in the face of constraints. So let's see how it looks. So one is on the sidecars. Now there is a tendency to add every new thing as a sidecar, which is fine, which kind of simplifies things, but it also wastes resources. Think of it this way: if there is something you can deploy on a host, or let's say observing your containers, but instead of deploying it on the underlying host, you deploy it in a sidecar of a container of the pod. There is a multiplicative effect, right? So let's say you have 10, let's say you have 100 containers, you are adding 100 more CPUs if the sidecar requires 1 CPU each. So that's one side. But also things like if your sidecar is often changing, you'll end up restarting Cassandra when your sidecar has changed. That's something we probably don't want to do. So things like that. And as much like the sidecar model, the goal here is to achieve balance. Add sidecar where it's absolutely necessary. Otherwise, see if you can do this remotely. Like for our repairs, instead of doing it with the sidecar, we decided to do it through Reaper, which is a centralized mechanism. Isolation. Isolation is much more important when it comes to containers. Keep in mind, even with EC2, you have what is known as guest stealing, wherein the guest on the same node can steal CPU. Whereas with containers, you are deploying even at even a higher level. So we need to constantly detect this. We have detection mechanisms for, let's say, Docker CPU throttling, and we keep an eye on that. Other than so on the CPU side, I feel like it's something manageable because Linux provides very good mechanisms for CPU and memory isolation, and it's constantly improving. We are also looking at newer kernels here, but also we do few things like page cache warming whenever we start a container, whenever we restart a pod. We also have deployed our cluster on EBS optimized instances so that the network traffic and the IO traffic do not contend with each other. Yes, and we also look at isolation from a scheduling and bin packing perspective as well, so that any something like so that when there's a lot of interference, let's say an IO, we can reschedule the pods to reduce this issue. Lastly, but very important aspect is deployment strategy. What is the point if you have all this, but you're not able to deploy things in production? So first things are like deployment pipelines typically are attuned to what are known as microservices deployment. Whereas at least at Yelp, we have this single image model wherein you have the same image which goes into from non-production to production. But when it comes to like databases, you need to be able to like experiment with different cluster images, like different versions. You don't want the entire infrastructure to move from one version to another in one jump, right? You want to make it more gradual and things like that. So this is something that we've been looking at. We've also been looking at Puppet on moving away from Puppet and Terraform for Cassandra, because that's how we have managed some of these configuration aspects, and seeing how we can best do it in container, and also dealing with immutability, which means that, so this is interesting, which is that in Kubernetes, you have many of these objects which are immutable in nature. Stateful set is immutable. But at the same time, some of the changes that we may be doing, let's say increasing the size of a storage, is something that's mutable. And in stateful set, that particular bit is considered as immutable, which means you'll have to recreate the stateful set while ensuring the cluster is running. So that is something we have figured out, and we are automating that as well. But that has been figuring that out has been quite interesting and empirically challenging, to say the least. Great. So we have covered the opportunities and challenges. Let's come to the conclusion. So to reiterate, I presume I made you a much better believer in these fallacies when it comes to orchestration of distributed systems, especially things like one administrator, because as you can see, something like our orchestration stack is managed on multiple levels and by multiple teams. So there's no one administrator. And the topology of Cassandra keeps changing because, when you deploy a new change, you have to restart everything. And if you have a client which is not comfortable with the constant topology change of your cluster, that's something that needs to be fixed in the operator. So let's end it with a quote. So I started with the quote from Leslie Lamport. Let's end it a quote on distributed systems as a Twitter-worthy quote. Again, I would. So it goes like, distributed systems are nothing but building reliable systems out of unreliable components. Unreliable components also include, but not limited to, humans. So this also applies to the orchestration system as well. So you need to ensure that your system is greater than sum of the parts. Anything and everything can fail at any point in time, but you still need to ensure that you keep the lights on and you keep the system going forward in spite of any challenges. And that culminates the talk. So let me know if you have any Q&A. I'll be also happy to take any Q&A offline, and you can also contact me, outside this talk. And these are the links for Yelp's various open source related activities. And these are the credits. Thank you.